Okay, for the purposes of the people watching the video, I forgot to start it, so you missed the first few minutes. We haven't done very much. We just looked at the first page of this textbook. Okay, we continue. Okay, so this is, we can skip most of this. Yeah, we'll skip this. We can skip that. Okay, so this is just something fun, but it kind of gets you into the spirit of doing mathematical proofs. So I said a second ago that the square root of 2 wasn't rational. Okay, so we said this set Q was the set of all rational numbers, and Q was equal to P over Q was equal to P over Q, where P and Q were in the integers. So how do we prove that square root 2 is not rational? So square root 2 is not in Q. So there are various techniques for proof that get used all the time in maths. And one of the most common is proof by contradiction. So what we're going to do is we're going to suppose it was the case that square root 2 was irrational,
Okay.
and then show that that leads to something impossible. And this is something that gets used all over the place. So suppose it was the case that square root 2 was in Q. So let's just write WTP means want to prove. So we want to prove this, that square root 2 is not in Q. So suppose suppose that square root 2 was in Q. Well, from the definition of Q, we know that that means that there must be some PQ. So let's use my notation. So it means there must exist some P and Q in the integers, such that square root 2 is equal to P over Q. Okay. So that's just from our definition of this set Q. So there must be some integers P and Q such that this is true.
Yeah.
You know, in general these integers might have some common factors. Okay, so maybe this is, I don't know, 100 and this is 50. We know that 100 over 50 is 2. We can get rid of common factors. So let's rewrite this as m divided by n, where these two things don't have any common factors left. Okay, so if you like, we've divided by both p and q by integers until what we're left with we can't divide by integers anymore without it becoming a fraction. Okay, you know, so suppose that p over q was let me think of 12 over 36. Well, you know, 12 is 2 times 6. 36 is 6 times 6. So this is that right? Yeah. So this is 2 divided by 6. Well, 2 is 2 times 1. 6 is 2 times 3. Okay, so this is one. This is very basic. Okay, but so we can always express p over q as some fraction m over n such that these two things don't have any common factors anymore. Okay, so then we know that square root 2 is m over n, so 2 must be equal to m squared over n squared. So 2m squared is equal to m squared. And then, well, this left-hand side is even. So if this is even, what do we know about m?
should be even, right?
Yeah, yeah. So the only way that m squared can be even is if m is even as well.
Yeah.
So m must be equal to 2 times, what do they use here? 2 times k. So there exists some k in z such that m equals 2k, right? So then we know that 2n squared equals 2k all squared, so 4k squared. Okay, so that 2k squared is equal to n squared, which is divided by 2. So then we divide by k squared, take the square root. We have that square root 2 is equal to n over k. Well, I'm sorry, I'm going down the wrong route. We don't need to go any further. From this, look at this, what do we know about n? From this equation?
It should be even.
Yeah. So this implies that n is even as well, but we said that m is even.
Yes.
And so we've got a contradiction, right? We said that m and n had no common factors, but we've proven that m is even, and now we've proven that n is even.
Okay.
So that's a contradiction. Okay, and when there's a contradiction, mathematicians make a sign like that for contradiction.
Okay.
So that completes the proof. Okay, if it was the case that square root 2 was irrational, square root 2 would be expressible like this with no common factors, which implies that m would be even, which would imply that n is even, which contradicts the assumption of no common factors. So that's a proof by contradiction. Okay. We'll use that a lot. Okay, you assume the opposite of what you're trying to prove. You know, so that's a very famous result. I don't know, it's one of, is it Euler proved it, or Euclid? One of the two. Euclid, I guess, for Greek. So what we proved from it is that square root 2 is not in the rationals, okay? But square root 2 is a real number, so it's in the reals. You know this notation, don't you? This moving on a bit, so
yeah.
that means the absolute value of. So if it's negative, you just get rid of the minus sign. Okay, and then yeah. So for a few theorems here, which are very easy. I don't know how well you can see this.
Yeah.
You can see okay?
Yeah.
Okay. So this is kind of trivial. For any number x, minus the absolute value of x is less or equal to x is less or equal to the absolute value of x. You know, if x is positive, then x is equal to the absolute value of x, which is certainly bigger than minus the absolute value. If x is negative, then x is equal to minus the absolute value, which is certainly smaller than the absolute value. Okay. So, kind of trivial. The absolute value of a product is the product of the absolute values. It's obvious. And then this inequality we'll use again and again and again. It's very important. So this is called the triangle inequality. And it says that the absolute value of a plus b is less or equal to the absolute value of a plus the absolute value of b. You've seen that before?
Yeah, I have, yeah.
Yeah. This is very easy. It's for real numbers. It's kind of obvious why it's called the triangle inequality. Is if you think in a two-dimensional space, then I think with vectors in a two-dimensional space. So here's one, here's another. So let's call this A, let's call this B, and this A plus B. So these are vectors. So this is a triangle, and the triangle inequality is saying that the length of this line is smaller than the length of that line plus the length of that line.
Yeah. Okay.
It's actually clearer in 2 dimensions than it is in 1 dimension. And how are we going to prove it? Well, the proof is, just clear the screen a second. So that didn't work. There we go, a bit of white screen. Okay, so the absolute value of a plus b, well, that's just the square root of a plus b squared. If you do a plus b squared, it's always positive. If you take the square root, then you still have something positive. Okay. So okay, so let's square both sides. Okay, so absolute value of a plus b all squared is a plus b all squared. Okay, which is a squared plus 2ab plus b squared. And a squared is just the same as the absolute value of a squared. But a times b is, ab is certainly less or equal to the absolute value of ab. We can always make it bigger, okay, so this is less or equal to a squared plus 2 absolute value of ab plus absolute value of b squared, okay. But we know that the absolute value of a times b is the absolute value of a times the absolute value of b. You can see what are we going to do next?
And this is a plus b.
Yeah,
Absolute,
exactly.
yeah.
Yeah, exactly. So this is absolute value of a plus the absolute value of b, all squared. Okay, which is what we wanted. Okay, so then we take square roots of both sides. We have that the absolute value of a plus b is less or equal to the absolute value of a plus the absolute value of b.
Yeah.
It's kind of trivial. And there's an immediate corollary to the triangle inequality. So a corollary is a word that mathematicians use all the time, and economists too. So so if you've proven a theorem, a big result, a corollary is a little result that follows from the big result. So suppose we have A equals D and B is equal to C minus D in the triangle inequality. Okay, when the triangle inequality says D plus C minus D is less or equal to absolute value of D plus absolute value of C minus D. But D plus C minus D is just C. Okay, so its absolute value of C is smaller than D plus C minus D. Okay, so absolute value of C minus D is bigger or equal to absolute value of C minus absolute value of D. The reverse is true as well. So if you do it with A is D minus C, and yeah. So A is C and B is D minus C. Okay, then you're going to get that D minus C is bigger than absolute value of D minus absolute value of C. But D minus C is equal to, absolute value of D minus C is equal to the absolute value of C minus D, because you just flip the sign. Okay, so we have the absolute value of C minus D is bigger or equal to the absolute value of the absolute value of. Okay, so we've got absolute value of C minus D is bigger than the absolute value of the absolute value of C minus the absolute value of D. Okay. So these are like outer brackets.
Yeah.
Brackets. Okay, so this is another form of the triangle inequality that we'll use quite a bit. So that was chapter 1, that wasn't so hard. So moving on, so the fundamental property of the real numbers, which won't be shared, which isn't shared by the rationals, say, is that if you have a set of real numbers and it's bounded above, then so if you have a set of real numbers and it's bounded above, then there must be some real number which is the smallest possible least upper bound for that set. Okay, and this chapter is about that property. And this is what distinguishes the real numbers from the rationals and from other sets. Okay, so what was one tangent? So for a set to be bounded, what do we mean? Well, if S is some set, we say that S is bounded if there exists L for lower, U for upper in R, such that for all little s in big S, for all elements of the set S, L is less or equal to S is less or equal to U. Makes sense, right? So there's a lower bound and an upper bound, such that for any element of the set, the lower bound is less than that element, which is bigger than the upper bound. Okay, you can see this notation is useful because you end up using it all the time. If this is true, then let's take B to be the maximum of the absolute value of L and the absolute value of U, then it must be the case that minus B is less or equal to S is less or equal to B. Okay, let's go through them. So we've got two things to prove. First, we've got to prove that S is less or equal to U. And then we've got to prove that L is less or equal to S. Okay. So let's do this one first. Okay. So we know that if S is less or equal to B, sorry, what we want to do is we want to prove that this implies that. So if this is true, then this is true. Okay, that's what we're trying to prove. So we want to prove we want to prove that s is less or equal to b. We want to prove if s is less or equal to u, then s is less or equal to b. Okay, so, well, if s is less or equal to u, then s is less or equal to the absolute value of u, because u is less or equal to the absolute value of u. But b is the maximum of the absolute value of u on something else. Okay, so b is certainly bigger than, at least as big as the absolute value of u. Okay, so s is less or equal to b.
Oh, okay, okay.
And the other way round, well, s is bigger than l. Well, l is bigger than minus the absolute value of l. Oh, yeah, yeah. You know, if l was 3, then this is minus 3. If l was minus 3, then this is minus 3. Okay. So l is bigger than minus the absolute value of l. But if b is the maximum of the absolute value of l and the absolute value of u, then minus b is the minimum of minus the absolute value of l and minus the absolute value of u. If you take, you know, so suppose this is 4 and 5. Okay, then the maximum of 4 and 5 is 5. So, but minus b is the minimum of minus 4 and minus 5. Okay, if you take minus of a maximum, you get a minimum. Okay, so minus b is certainly smaller than minus absolute value of l.
Okay.
So what we've proven is that a set of real numbers is bounded if and only if for some number such that the absolute value of all of the elements is less or equal to that number. Okay, so so this continuum property that I stated at the start with is stated here. So any set of real numbers which is bounded above, which has some, so to be bounded above, set S is bounded above if there exists some upper bound in the reals, such that for all elements S of the set S, S is less or equal to U. Okay? U doesn't have to be in the set necessarily. So, for an example that's going to be useful, think about the set S is a half plus 3/4, a half, 3/4, 7/8, 15 over 16, etc., etc. Okay, so it's a set with infinitely many elements. 1 isn't in the set. Okay, every element of the set is less than 1, but we know that 1 is going to be an upper bound to that set. Okay, and in fact it's going to be the least upper bound, because these elements are going to get progressively closer and closer to 1. Okay. So the continuum property says that any set of numbers which has an upper bound also has a least upper bound. And if we had more time, we could go through. You can actually prove this from axioms. So for axioms for real numbers, you can prove it. So for this least upper bound, we call the least upper bound the supremum. So you've probably seen this. So we write that using its notation, we write B is sup. So this is one notation. This is the supremum of all x where x is in S. Okay, so this is the least upper bound. Supremum just means least upper bound. And inf means smallest lower bound. Okay. Okay, so if you've got a least upper bound of, so another way you can write it is like this: B is just sup S, supremum of the set S. If B is the supremum of the set S, we can create a set minus S, where we just take the minus of each element in the set. Okay. So suppose that B is minus the supremum of the set minus S. Okay, so this set minus S, we just flip the sign of every element of the set S. Okay. So this is the least upper bound of the set minus S, and this turns out to just be equal to the smallest lower bound
Okay.
of the set S. And we'll prove that in a second. Okay. So if the set has a maximum, then we write max S for the maximum element of the set, min S for the minimum element of the set. Okay, but not all sets have a maximum. So that set of elements I showed you before, with infinitely many elements, it doesn't have a maximum because for any element there's another one which is bigger.
Yeah, okay.
Okay. So if a set does have a maximum, then the maximum will equal the supremum. Okay, so for example, here's the set 1, 2, 3. Well, the maximum of that set is 3. 3 is also an upper bound for the set. Okay, every element is less or equal to 3, and it's the smallest possible one. There can't be an upper bound that's below 3. Okay, so if there's a maximum, then that value is also the supremum. Really. So to give us a slightly more formal definition, so we say that B is the supremum of the set S if. So two things have to be true. It has to be an upper bound and it has to be a least upper bound. So for it to be an upper bound, it must be the case that for all S in S, for all that, little s is an element of the set big S. S is less or equal to bin. Okay. So every element of a set is at least smaller than this thing B. And it has to be the least upper bound, okay, which means for every x less than b, so for anything less than b, that can't be an upper bound, okay. So how do we say that something isn't an upper bound? Well, if something isn't an upper bound, this thing must not be true. Okay, so this says for all elements of the set, they're smaller than b. If we want to take the negation of a for all, that's there exists. So if it's not the case that this is true, there must be at least one element for which it's not true. Okay.
Yeah.
You know, so I don't know, if you want to prove, if you want to prove that it's not the case that all cats are black, all you've got to do is find one cat which isn't black, okay? So this is, there exists S in S such that this thing isn't true, so the opposite of less or equal to is greater than, S greater than B. And this is a useful property. Okay, if you're taking the negation of a for all, you always get an exists. If you're taking the negation of an exists, you always get a for all. Okay, so if it's not the case that there exists a white cat, then all cats must not be white. Okay. So something is the least upper bound if these two things are true. It's the supremum if these two things are true. So if there was an exercise there, okay, so the similar thing for an infimum, well, little b is the infimum of S if similar things. So tell you what, why don't you have a go at telling me what the definition of an infimum would be by n log to n?
For every for every S which is in S,
Yeah.
right? S should be greater or equal. Say
Yep.
be small, right?
Yeah.
So this is the first, yeah.
Yeah.
Okay, and the second one will be for every Z maybe, which is greater than B small.
Yeah.
Very exists.
Yeah.
S small, right? Yeah, which belongs to S. S large, such that S is smaller than the B small.
Yeah, exactly. So, so can we use these two definitions to prove that B is equal to minus sub minus
Okay.
S? So, this is what we want to prove. So, any ideas for how we might prove this?
Yeah.
So, one way might be by contradiction. So if we wanted to prove this by contradiction, what would we do?
So yeah, we start that we assume that exists, that is true, and
No, so to prove by contradiction, we assume the opposite. Okay, so we can assume that B is assume B not equal to minus the supremum of minus S. Then not equal, if something is not equal to another thing, there are two possibilities. It's either bigger than or smaller than. Okay, so we're going to have two cases. So the first case means B is bigger than minus supremum minus S. Then what do we know? Minus B is bigger than the supremum of minus S. So remember, the supremum is the least upper bound. This is bigger than every element of this. This is minus B is even bigger. Okay, so minus B is an upper bound for minus S. Okay. So supremum is bigger than every element of minus S. Here we've got something that's even bigger. Okay, so it certainly must be the case that for all S in S minus B is bigger than minus S. Well, this is our one here, so it's not good enough, is it? That was true, but not what we need. So,
maybe the last equation, it should be minus b smaller, right?
well done.
Yeah.
Yeah. Makes sense. I'm not awake. Yeah. So whenever you apply a function which is an increasing to both sides of an inequality, you flip the signs again. Glad you were paying attention. Okay. So yeah, that makes sense. So minus b is smaller than. So that means that this is the maximum. So this is smaller than the maximum. Well, it's not. It's the supremum. So by the definition of the supremum, so what we've got is we've got some element that's less than the supremum, and let's look at the second property of the supremum. This says for anything less than the supremum, there is an S satisfying this. Okay, so we know that minus b is less than the supremum, so this must be true. Okay, so it must be true that there exists some S in S such that look at this S. Sorry, our set was exists minus S. Okay, we're applying it to the set minus S. Such that S is in S is greater than our supremum oh god, my definition is wrong. Sorry, the definition was wrong.
Okay, so
not paying attention. Let's go back a second. So this is supposed to say for anything less than the least upper bound, the supremum, there must be some element of the set which is bigger than that x.
okay.
So if we think about this set again, half, 3/4, 5/8, 15, 16, etc. Sorry. So suppose we thought that 15 over 16, suppose we thought that 5 over 8 was the supremum. Well, can it be? Well, according to this, if 5 over 8 was the supremum, so suppose we thought 2 was the supremum of this set. Okay, we know that the supremum is actually 1, right? Suppose we thought that 2 was the supremum. This says for any x less than our upper bound. I still don't know what the definition right, have I? God. No, this is fine. Okay, so if we thought 2 was the least upper bound, this would say that for any x less than 2, so let's take 1.5, there should be an element of S which is bigger than 1.5. Okay, but there's no element of this set which is bigger than 1.5. Okay, because they're all less than 1. Whereas if we take 1, which is the true least upper bound, which says for any x less than 1, so I don't know, 0.999, the sum element of a set which is bigger than 0.999. And if we carried on, eventually we'd get something that was bigger than 0.99.
Okay.
Sorry, I made a mistake. Wake up then. Okay, is that clear? Okay, do stop me if I confuse you. I make slips occasionally. Okay, so going back to this, we'd shown this, that minus b was less than the supremum of this set minus s. So we can apply this second property of the supremum. Okay, minus b is something that's less than the supremum. Therefore, there must exist some element s in the set minus s, such that s is greater than the thing we started with, which was minus b. And change things slightly. Let's call that x. Things a bit clearer. Okay, so x is in the set minus s. Therefore, there must exist some s such that x is equal to minus s. Okay, because the set minus s is just this set. It's minus s, s in s. Okay, that's the definition of the set minus s. Therefore, if x is in the set minus s, then, well, there must be some s in s such that x is equal to minus s. So, this means there exists s in s such that minus s is greater than minus b. Flip the signs, so we have s is less than b. Not making the same mistake again. So what have we shown? Okay, so some element of s was smaller than b, but b is supposed to be the infimum of s. Okay, so in particular, for every element of s, s is bigger than b, but here we've proven s is less than b. Some element of s which is smaller than b. Okay, so in this case we've shown that b isn't even a lower bound, let alone the greatest lower bound. Okay, so this has led to a contradiction. So this first case leads to a contradiction. We then have to do the same thing for the second case. So the second case should be easier, I think. So case 2. So we started by assuming that b was not equal to minus supremum of minus s. So one case with b was bigger than, the other case must be b is less than minus sup minus s. So then the same thing again, minus b is greater than sup minus s. So here we've got some element that's bigger than the supremum. So the supremum of minus s is only bigger than every element of minus s. So minus b must be bigger than every element of minus s. Okay, so this means for all s in s, minus b is strictly greater than minus s. Okay, so b is less than S. Okay. So, well, this is okay, isn't it? This is saying B is a lower bound. So this isn't where we're going to get the contradiction. Let's go back to this. So let's look at this property of the infimum instead. That's more useful. So the second property of the infimum says that any z bigger than b, there must be some s such that s is smaller than b.
Then this z, should be
yeah,
z.
exactly. So here we've got this thing is our potential z. Okay, so this then says that there exists s in S such that S is that should be Z. Shouldn't it? So it's S and S. Okay, we're applying this. B is the infimum of S, so we're applying this to the set S here, whereas there we applied it to the set minus S. So just straightforward from here, there exists S and S such that S is less than our Z, which was this thing, minus sub minus S. So minus S is greater than sub minus S. Okay, now hopefully this works now. So then for all x in the set minus S is greater than minus x. Okay, so S is less. Okay, so for all t in, so if x is in minus S, you mess all over the place. So minus S was bigger than the supremum of this set minus x. So this means that minus S is bigger than every element of this set minus x. But the elements of the set minus S are just minus the elements of the set S. So for every t in S, minus S is bigger than minus t. Okay, but S was in S. So in particular, we have a contradiction because we know that S is in S. So if we apply, this is true for all t in S, let's apply it for a special case when we suppose take t, or we take t equals S. We take t is equal to S, then this says that minus S is greater than minus S, which is clearly impossible, which is a contradiction. I made a bit of a mess of that. Okay, so this is how mathematical proofs go. You know, you'll go down the wrong route occasionally, but you work out you've gone down the wrong route, and then you can kind of backtrack and work out what you need. So this is quite a common structure for a mathematical proof. You prove by contradiction when you get a load of cases, and you take each case separately. And then I think this is the kind of thing they want us to go through in this course, because you know you're going to be seeing a lot of proofs, and you know, it just helps to be familiar with the types of proofs that you see and techniques you can use for proving things. And the more you see, the more familiar everything starts to look after a while. Yes, we've kind of covered this. This I presume you know. So this notation, A, B, means for set of all real numbers between A and B, not including either A or B. With square brackets, that means for set of all real numbers between A and B, including A and B. Yeah, have you seen this? With one square bracket and one round bracket, that means set of all numbers between, including A but not including B, etc., etc. Okay, you can write it in set notation like that. And people also write things like this: A, comma, infinity. And infinity always has a round brackets because you never actually include infinity. And infinity is not a real number, but you know, it's just a special notation. This it's not that we're treating infinity as a real number. You have to be a bit careful. Infinity not in. So what do we have to say? So if we do this one as well, A, B, round, square, these are the four types of bounded intervals. Again, from 4 endpoints we can potentially include. And then we have 4 types of unbounded intervals. Okay, you're always not including infinity, but you can either include or not include the start point, and you can either be unbounded at that side or unbounded at that side. So we've got 4 types of bounded intervals, 4 types of unbounded intervals. This is called a compact interval. Okay, and you'll see where this terminology comes from a bit later. It's also called a closed interval. This one is called an open interval, okay, and A infinity and minus infinity A are also open. So when you have round brackets everywhere, we call it an open interval. When you have a mix of round and square brackets, we call it a half open or a half closed interval. Okay. Why they matter will become clear. What's this giving? This is just giving a few properties of supremums and infimums. So, seems like a lot of work. We won't go through the proof. So this is proving that if you've got some set and some positive number xi, then the supremum of xi S is equal to xi times the supremum of S. Okay, I can't draw that Greek letter, it's kind of a squiggle.
It is a Greek letter, right?
It's a Greek letter.
C.
Z.
C, yes.
Okay. Okay. You're Greek, are you?
Yeah.
Okay. Okay, that's better, isn't it?
Yeah.
See. I tend to just draw a vague squiggle and not worry too much. So this is saying that the supremum is a linear operator. Okay, if you multiply every element of the set by something, then the supremum of that is the original thing times the supremum. It's kind of intuitive, right? I suppose we can just go through the proof in the textbook. So they take B to be the supremum of S, So then B has this property. Okay, so this is saying B is an upper bound. That's all they're saying there. And here's this. They're calling this set ZS. We call it T. Okay. So then because x is less than or equal to b, multiply both sides by z. Zx is less than or equal to zb. So zb is an upper bound from set T. Okay, so the first property of the supremum is satisfied. Now we just have to show that it's the smallest upper bound. So it certainly has the smallest upper bound. That's the continuum property of the real numbers. Okay, so call the supremum of this set T. They're calling the supremum C. So they know that we know that ZB is an upper bound. So it certainly must be the case that C is less or equal to ZB. Okay, C is the least upper bound, so it's certainly less or equal to any particular upper bound. So if we swap the roles of S and T, what's it saying? So for any, well, yeah, okay. So we know that for any element of this set T, any element Y of this set T, Y must be less or equal to C, this least upper bound. So Z inverse of Y is less or equal to Z inverse C. Yeah. But yeah, this is quite a clever proof. So just as if we take Z inverse of T, well, that must be equal to the set S. Okay, if S is the set Z of S, then what? T is the set Z of S, then we pre-multiply both sides. Okay. So we know that Z inverse Y is less or equal to Z inverse C for any element Y of T. Therefore, Z inverse C is an upper bound for T. This set Z inverse, the elements of the type that form Z inverse Y, that's just S. Okay. See, so these elements. So if Y is in T, then Z inverse Y is in S. Okay. Okay. So for every element Y of T, Z inverse Y is less or equal to Z inverse C. Okay, but Z inverse Y is just the elements of S. Okay, so this is saying that all of the elements of S are less or equal to Z inverse C. Okay, so Z inverse C is an upper bound for S. So because B is the least upper bound, it must be the case that B is less or equal to Z inverse C. Okay. So Z times B is less or equal to C, but we're already proving that C is less or equal to ZB. Okay, so B must be equal to C. You could do this proof by contradiction as well. Yeah, let's get through this chapter then. Break. Okay, so these are the basic properties of the real numbers. This chapter just covers the basic properties of the natural numbers. Okay, so the counting numbers, 0, 1, 2, 3, 4. Basic property of the natural numbers is they're unbounded above, and you can prove it by, if you like, an axiom that if n is a natural number, then n plus 1 is also a natural number. And it's kind of trivial, we won't go through it. Okay. So, what do I say? Every set of natural numbers which is not empty has a minimum. Well, we'll go through this very quickly. So if you've got some set of natural numbers, S, so you certainly know that naught is a lower bound for the set S, okay, because every natural number is at least as big as naught. So it must have a largest lower bound, possibly a real number, not necessarily a natural number. So let's call the infimum the largest lower bound B. Then B plus 1 is not going to be a lower bound. So there's some natural number n in this set where n is less than B plus 1. Okay, just otherwise n would be a lower bound, right? So there are two possibilities. Okay, either n is the minimum of S, in which case we found a minimum for the set S and we're happy, or it's not the minimum. If it's not the minimum of the set, then for some element m in the set S, which is smaller than n, so then you get the inequality they have there, which we rewrite for you. So B was our infimum. So B was our infimum. We started off by saying that B plus 1 was not an infimum, so there must be some element n less than it. And we said that n wasn't a minimum, so there must be an even smaller element, m. And m must be bigger than b because b is at least a lower bound for the set. So m is in the set S, so it must be bigger than b because b was a lower bound for the set. Okay, so we have this inequality. But then
then we have 0 smaller than 1, right?
Yeah. Well, not. So the problem is that so b could be equal to m, but if you like, the distance between m and n must be at least 1, and the difference between n and b must be at least 1. Okay, so here we must have increased by at least 1, we must have increased by at least 1. So here b must be b plus 1 must be at least 2 bigger than b, but b plus 1 can only be 1 bigger than b. How can we make that a bit clearer? Yeah, I think it's just that. So
okay.
You see what I mean? So
yeah.
So this is a strict, so suppose this is 5. This is like 5, 5, so this must be at least 6.
Yeah.
This must be at least 7, so
Yes.
this is 5 and 7, but 5 plus 1 is equal to 6, not 7. Okay, so every time we have a strict inequality, we must be going up by at least 1. Okay, which gives us a contradiction in that case. Okay, so only the case in which n is a minimum can be true. It's kind of obvious, right? So, a lot of maths is proving obvious things, but occasionally you prove something surprising. So, yeah, every set of natural numbers has a minimum. Doesn't necessarily have a maximum, but at least has a minimum. None of those. Okay, now this is very important. So proof by contradiction is one type of proof you see all over the place in maths. Proof by induction is another type of proof that you see all over the place. And what proof by induction says is, suppose for any number p of n, for any number p of n is some statement, okay, which is a function of n. So p of n might be I don't know. Let me think of something we might want to prove. Do you know that theorem? Yeah, that's the binomial theorem. So this is a theorem, and it's a function of n, right? This holds for n is 0, it holds for n is 1, it holds for n is 2, etc., etc. Okay, so let Pn be the statement that that equation is true when n is 0, or when n is 1, when n is 2. Okay. So this is just an example. There are lots of things that you might like to prove by induction. So Pn is some statement, and what the principle of induction says is, suppose you know that P0 is true, so you can prove P0 is true, and you can prove that if Pk is true, for some k in n, so if for some natural number k, such that pk is true, then pk plus 1. Okay, so if pk is true, then pk plus 1 is true. So suppose you can prove these two things. One, that p0 is true, and two, that if it was the case that if pk was true, then it would also be the case that pk plus 1 was true. And what the principle of induction says is that these two things put together imply that for all k in the natural numbers, pk is true.
Okay.
It's kind of so if you know, if you like it, it's justifying going to infinity. So you know, if we know p0 is true, then from the principle of from this second property, we know that p1 is true. If we know P1 is true, then we know that P2 is true. If we know P2 is true, we know that P3 is true, etc., etc. So, you know, it's kind of intuitive that these two things imply this. And this is a property of the natural numbers, if you like. And when we want to say if then, we normally just do an arrow. So an arrow means if then. So we could write that so we can write pk implies so it would be for all k in n, pk implies pq. So if we can prove these two things, then we know that. We're not going to do that. Okay, let's do that example. So let's prove. Let me just remember what. So just as an example of proof by induction, have you seen this before? You know this notation for sum. K is 1 to n. So this is, you can, is that right? Yeah. Just copied it from there. Yeah, it is. So there's a kind of intuitive proof of this, which is, well, look at this sum. So if you have, I don't know. So take that. So we can take pairs of elements. 1 plus 4 is 5. 2 plus 3 is 5. If we had another element on the end, 1 plus 5 is 6. 2 plus 4 is 6, and then we have 3 that's left over. So if you like, the average is always the same. So the average of 1 and 5 is 6, the average of 2 and 4 is 3, and then we've got the 3. So we've got, how many of these pairs have we got? Well, we've kind of got 5 elements, and we've got 2.5 pairs. And each of them has an average of 3. Okay, so if you like, if we have n, then we have n over 2 pairs, and each of them has an average of 1 plus n over 2. So we, I didn't quite explain that right. So we have, in total we have 5 elements, but it's just that we can rewrite them like this: 1 plus 5 plus 2 plus 4 plus 3. So we've still got 6 elements, but because we know that these pairs are averaging to the same thing, it's like having 3 plus 3 plus 3 plus 3 plus 3. Okay, and so it's like we've got n copies of the average. Okay, so the average is 1 plus n over 2. The average of the first and last is 1 plus n over 2. So it's like we've got n times 1 plus n over 2. So that's kind of the intuitive way of showing this. Let's do it a bit more formally by reduction. So when n is 0, what does this say? Well, the sum from k is 1 to 0 is just an empty sum, which is 0. Okay, the right hand side is 0. So when n is 0, we just have 0 is 0. That's fine. Okay, so let's suppose that we know it's true for some n. So this is our Pn, this thing here, that statement. So suppose Pn, and let's see if we can prove Pn plus 1. Okay, so if we know Pn, then we know that sum k is 1 to n is half n times n plus 1. Okay. What we want is the sum k is 1 to n plus 1. Okay, well that's just this plus n plus 1, right? There's an extra term on the end. So this is sum k is 1 to n k plus n plus 1. Okay, well that must be equal to half n plus 1 plus n plus 1. So we have another copy of n plus 1, right? So it's like we have half n plus 1 n plus 1. And half n plus 1, well that's just equal to half of n plus 2. Okay, but, well, let's just rewrite this the other way around, so that's half n plus 1, n plus 2, but that's just, so what we've proven is Pn plus 1, right? So if we replace n with n plus 1, replace n plus 1 with n plus 2, okay? So we've proven that sum k is 1 to n plus 1 k is equal to this thing, okay, which implies, and arrow means implies, Pn plus 1. So if Pn is true for some n, then Pn plus 1 is true. Okay. Therefore, by the principle of induction, for all n. Does that make sense?
Yeah.
So, something that's quite useful, and you'll see it used again and again. Yeah, so some results in econometrics you'll prove using induction. Okay, we won't bother with that. Won't bother with that. Okay, let's look at this. No, let's take a break. This isn't too. So we'll have a 5-minute break.
Yeah.
Does it make sense?
Yeah, I just need some time to go through it and.
Well, do tell me if you don't.
Yeah, sure, yeah. No, I'm fine. For now, I'm fine. Yeah, thank you.
It's going to be quite intense, but it's. Hopefully you'll find it's useful to have had this week to do some maths. I guess it's a long time since you did any maths, so.
4 years.
Yeah. And then just get back into it again. Okay, I'm going to get some water.
Yeah.
nothing in there on Monday, and you've got Antonio, Martina, nothing on there. It's a bit better next week. You can do some work in between next week. And then, okay, and then, yeah, and just check to see if any of them, because Martina, what day is she? Oh, she's Tuesday day. What day is she? Yeah, she's Wednesday, Tuesday. So you need to check where they are. All right, you're very welcome, Andy.
You're cold.
Yeah, a bit.
Not sure what we can do about it.
Well, in general, I am cold, so
It's this country.
yes.
Okay, where were we up to? Sequences. Yes, you might have done this in high school.
Mhm.
Some people do.
Yeah.
It's a long time ago, I guess. So a sequence is just, you know, something like x1. Well, I don't know. They normally start at 0. This book throughout starts with things at 1 rather than 0. So, you know, this is a sequence: x1, x2, x3. Okay. So it's just a number for each of a real number for each of the natural numbers. Okay. People often write this notation. They might just write xn in brackets for the whole sequence. Sometimes they write xn, n is 0 to infinity. Sometimes they write xn, n in n. This book uses slightly different notation. It uses angle brackets like that. Angle brackets aren't very standard notation, to be honest. So these are kind of the normal notations. So if you have a sequence, there's a set associated with a sequence, which is the range of the sequence. So it's the set xn, which for n in n. So this is, you know, these two things aren't the same. Okay, so the sets aren't ordered. Okay, so sets are just bags of elements in no particular order. You know, for example, think about the sequence xn is -1 to the power of n. Okay, so x0 is 1, x1 is -1, x2 is 1. So you get 1 minus 1, 1 minus 1. Okay, so this set, the range for it, will just be the set 1 minus 1. Okay, so this only has 2 elements, but the sequence is still defined over infinitely many elements. And what we're interested in mostly is whether sequences converge or not. Okay, so the sequence -1 to the power of n doesn't converge. It goes up and down forever. But, I don't know, the sequence xn is 1 over n, that converges to 0. Right? It gets closer and closer to 0. So we need a definition of convergence, and there's a kind of wordy definition. So given any small number epsilon, we can find some natural number, capital N, such that for any point in the sequence past this big number, capital N, the difference between the value of the sequence and the limit is less than epsilon. Okay. And normally we write this using symbols. Okay, so write for all epsilon greater than 0, there exists capital N in the set of natural numbers. Okay, so no, this is double struck, this is the set of natural numbers, this is N, just some big number, such that for all N greater or equal to big N, xn minus L, the limit, is less than epsilon. Have you seen this definition before?
Yeah.
So, it just means that if we're sufficiently far along in the sequence, then the difference between the sequence and the limit is sufficiently small. Okay, and by going far enough along, we can make the difference arbitrarily small. Okay, so even if epsilon is 0.00001, if we're far enough along, it can be very small. So, any of these examples worth doing? Okay, so let's just prove that, very simple example, let's prove that 1 over n converges to 0. Okay. So but what we normally write is, rather than writing all of this, we write xn tends to L as n tends to infinity. So what we want to prove is that 1 over n tends to 0 as n tends to infinity. Okay, so these proofs in analysis, this field of maths that we're looking at, they almost always start the same way. And they always start by saying, let epsilon be bigger than 0. Okay, so mathematicians have jokes about let epsilon be bigger than 0. You write it so often in maths. Okay, so let's take some epsilon bigger than 0. What we want to prove is that this is just an arbitrary number. We want to prove that this bit holds, that there exists some n such that for all n exists a big N such that for all little n bigger than big N. This is true. Okay, so what we need is that xn minus the limit is less than epsilon. Okay, xn is 1 over n, the limit is 0, so what we need is that 1 over n minus 0 is less than epsilon. Absolute value of 1 over n. So, which is true if and only if. So this double-sided arrow with heads on both sides means if and only if. So that implies that implies that. So this is true if and only if 1 over n is less than epsilon, which is true if and only if n is greater than 1 over epsilon. Okay. So n is positive, so the absolute value of it is just equal to the thing, so we can get rid of the absolute value signs.
Oh, okay.
Yeah. And if 1 over n is less than epsilon, then if you flip both sides, you also have to flip the inequality. N is bigger than 1 over epsilon. So it's kind of easy, isn't it? So all we need to do, take capital N equals 1 over epsilon plus 1. So capital N should be a natural number, really. So strictly, we should just take any natural number that's bigger than 1 over epsilon. Okay, but we know the natural numbers are unbounded. We showed that to start with. So there is a natural number bigger than 1 over epsilon. And then for any n bigger or equal to capital N, well, if n is bigger or equal to capital N, then it's also bigger than 1 over epsilon, so, which implies 1 over n minus naught is less than epsilon. So that will do. Okay, so we worked backwards a bit, we worked from the end to give us a clue about what we needed to guess, what we needed to take for this capital N, and then we can work forward. This isn't that way. Does that make sense?
Mm-hmm.
Good. Okay, should we do any other examples of this? Okay, so it's helpful if you know one sequence converges, then it'd be good to know that if you take combinations of sequences, they also converge. Okay, so this theorem has 3 parts. So the first one says if lambda and mu are some constants, xn and yn are 2 sequences, xn converges to L, yn converges to M. Okay, then if you take this linear combination, lambda times xn plus mu times yn, that converges to the linear combination of the limits. Product of series converges to the product of the limits. Ratio of series converges to the ratio of limits, as long as the bottom one isn't converging to 0. And, well, we'll have a go at these. So we have, so suppose xn tends to L and yn tends to M as n tends to infinity. Okay, so the first thing we want to prove is that lambda times xn plus mu times yn tends to lambda times L plus mu times M. So, how would we start this proof, do you think?
No, I'm just, what is that want to prove?
Yeah, so we want to prove this thing.
Mm-hmm.
So this is like an assumption. So suppose we've got one sequence xn which converges to L, another sequence yn which is converging to M. Then we're going to prove various properties about the combination of xn and yn. Okay. So this is one combination we could take a linear combination of the sequences.
Okay.
Let's check if this is what we call like. Okay, so how might we start?
Do we do it as before? We start from...
Yeah. Yeah, so the first line is going to be the same.
Yeah.
So we know that xn converges to L and yn converges to M. Okay, so given our epsilon, we know something about. Okay, so given our epsilon from these two facts, okay, we know from the first one we know that there must exist some capital N in N such that for all n bigger or equal to capital N, absolute value of xn minus L is less than epsilon. And from this one we know that there must exist some capital N in N such that for all little m bigger or equal to capital M, oops. I shouldn't use m, should I? Let's call this big N1. Okay, and then we'll have exist big N2 in N. So that's just for definition, just following immediately from what we're assuming. Okay. So this is what we want to prove, and the trick is going to be to take an n that's bigger than n1 and n2. Okay, so let's take n equals to the maximum of n1 and n2.
Why we have taken that?
Because if we take n bigger than the n equal to the maximum of n1 and n2, then for all n bigger or equal to n, we know both of these things are true. Okay, for all n bigger than n1, this is true. For all n bigger than n2, this is true. So for all n bigger than the maximum of the two, both things are true. Okay, so we know that xn minus L less than epsilon and yn minus M less than epsilon. What we want to prove, okay, so let me write it again. What we want to prove is that lambda xn plus mu yn minus lambda L minus mu M is less than epsilon. Okay. Well, we're not going to quite prove that. So we want a bound on this. I'm not going to say exactly what we want, but what is this thing? Well, we can rewrite this thing. So here's that minus that. This is what we've got here. So I can kind of write it, make it even clearer, put it in brackets like that. Yeah, that's fine. This is equal to. Let's put the brackets a different way. This is lambda xn minus lambda L. Brackets close. Plus, brackets open, mu yn minus mu m, brackets close. So this, if you like. So, do you remember the triangle inequality?
That is less or equal
Yeah.
to L xn. Yeah, the first one.
Yeah,
Yeah,
exactly.
absolute first one.
Yeah.
Plus absolute the second. Yeah.
So this is why the triangle inequality is very useful. and we know that, okay, remember that the absolute value of A times B is the absolute value of A times the absolute value of B. Okay, so this is equal to the absolute value of lambda times xn minus lambda plus the absolute value of mu times yn minus m. Okay, but for all n bigger than n, we know that xn minus l is less than epsilon and yn minus m is less than epsilon. Okay, so this is less than absolute value of lambda times epsilon plus absolute value of mu times epsilon. Okay, which is just absolute value of lambda. Okay, so now we've kind of done this. We haven't quite got what fits into the definition, right? Ideally we would have liked this to have come out as just being less than epsilon. Whereas in fact we've got it coming out as some constant times epsilon. But let's just take, so this is true for any epsilon, all of what we've done. Let's take epsilon equal to E divided by absolute value of lambda plus absolute value of mu, okay, which is also positive. Okay, if E is positive and this is positive, because this is positive. Okay, so if we take epsilon equal to that, then what we've proven is that this thing is less than E. So we kind of rewrite the proof as let E bigger than naught, okay, set epsilon equal to this thing, then all of this falls through. We have that this is less than E, okay, so we've proven it. Okay, so we've proven that this thing tends to that thing.
Okay.
Does that make sense?
No, there we have let E, and there it is epsilon greater than 0, right?
Yeah, so we've kind of done the proof in a bit backwards, if you like, but it's the clearest way of doing things. So we started off by taking any epsilon bigger than 0, any real number bigger than 0, and we showed that implied that this thing was less than that. Yeah. Okay. So what we're going to do is we went back to the start and we added in a few extra lines at the start of our proof. So now rather than starting by saying let epsilon greater than 0, suppose we started by saying let E greater than 0, and then we defined epsilon to be E over lambda plus mu. E is greater than 0, absolute value of lambda, absolute value of mu, these are positive, so this is greater than 0. Okay, so then everything we've got falls through with this definition of epsilon. Okay, so we know that this thing is less than E. Okay, so we've proven that for any E greater than 0, there exists a capital N such that for all little n bigger than capital N, the difference is less than E. And the fact that we're now working with E rather than epsilon doesn't make any difference, we're just renaming things. Okay. So it's a slightly backwards way of doing the proof, but it kind of makes it, you know, you don't, until you get to the end, you don't really know exactly what you need at the start. So it's kind of easier to do it slightly backwards. If you're doing it, I don't know, if you're doing this in a published paper, you would start here, right? You'd start with E greater than Z. So, you know, the point is that epsilon is arbitrary, so you can set it to be anything you like. So this was the first thing. So we've proven that linear combinations of series go to the linear combination of the limits. The other thing we had was that products of series go to products of limits. So xn, yn goes to L times m. And again, we're going to start exactly the same way. So for some, any epsilon greater than 0, we know that for n1 and n2, such as this holds, so for n equal to the maximum of the 2, both of them hold, just as before. So we want to bound on xn, yn minus lm. So this is where things get a bit tricky. So one trick with the triangle inequality is that, so the triangle inequality is like the most useful inequality in analysis. You use it all the time. But it's not immediately obvious that we can apply it here, right? So one trick that often helps is to add something and then take it away again. So add extra terms then that just cancel out. You know, what we want it to look a bit like, well, not quite sure. Let me see if I can remember this. So xn, yn minus xn n plus xn n minus m. So this is what we want to bound on.
Yeah.
Okay, we want to bound the distance between our series, which is xn, yn minus the limits. So what I've done is I've added xn times m, and I've added xn times m, and I've subtracted xn times m. So this is the same thing. I've just added and subtracted. But now we can apply the triangle inequality. Okay, so we're going to apply the triangle inequality on these terms and on these terms. So this is less or equal to absolute value of xn, yn minus xn m plus absolute value of xn m minus lm. Then we can take out the factors here. So we've got an xn here, we've got an m there. So this is just equal to absolute value of xn times yn minus m plus absolute value of m times xn minus l. Okay, so now we need, so this term, so okay, this term over here isn't too problematic. Xn minus L is less than epsilon, and m is just a constant, so it's fine. But here we've got this thing which is less than epsilon times xn. So you know, this is a function of n, so this is a bit problematic. So what we'd like is we'd like an upper bound on xn. But well, so this thing here, so we have the absolute value of xn minus l is less than epsilon. And it sometimes helps to draw things on the line. So if here's the limit, here's L, here's L minus epsilon, here's L plus epsilon. Okay, so what this is saying, absolute value of xn minus L is less than epsilon, is saying xn is somewhere in this interval, between L minus epsilon and L plus epsilon. So in particular, xn is less than L plus epsilon. Can I show that another way? Well, yeah, so if the absolute value of xn minus L is less than epsilon, then, so let's just write, xn minus L is less than epsilon. Well, xn minus L is certainly less or equal to the absolute value of xn minus L. And either this is positive and it's equal, or it's negative and it's smaller. Okay, so xn minus L is less than epsilon, so xn is less than L plus epsilon.
Okay.
Another way of proving the same thing. Yeah, so whenever you see a term like this, absolute value of xn minus L is less than epsilon, you know, it's helpful to have this diagram in your mind. It just means that xn is in this interval between L minus epsilon and L plus epsilon. Yeah. Okay, so if xn is less than L plus epsilon, then the absolute value of xn is less than the absolute value of L plus epsilon. Yeah, ideally we want a bound which doesn't contain an epsilon, but we also know that, okay, so this is for all n bigger or equal to capital N, this is true, right?
Okay.
Or capital N1. But for finitely many elements, so if you like, this is a subproof in our whole proof. So we're just looking at this first sequence. Okay, so for all n bigger than n1, absolute value of xn is less than L plus epsilon. Let's just take epsilon, just for a second, let's take epsilon just equal to 1. Okay, so then for some capital N1 such that for all n bigger than this number, xn is less than L plus 1. But then n1 is some finite natural number. So we can also take the maximum of xn between 0 and n minus 1. Hi, Vasco.
We can work on it.
So let's let capital M equal the maximum of absolute value of xn. It's supposed to be an x max for n less than n1. Okay, this is a finite set.
Mhm.
So this is a maximum over a finite set. So it exists. Finite sets have maximums. So for any n less than capital N1, xn is less than n. Absolute value of xn is less than n. For any n bigger or equal to n1, absolute value of xn is less than this thing, L, absolute value of L plus 1. Okay, so this means that if we take B is equal to the maximum of M and absolute value of L plus 1, then for all n in n, absolute value of xn is less than B. Less or equal to. So this is just a little kind of sub-proof. What we've proven here is that any convergent sequence is bounded. Any convergent sequence is bounded.
Mhm.
Okay, maybe I'll draw a picture to show you. So, if you like, what our little sub-proof was doing, suppose here's our sequence. I don't know, yeah, okay, it's converging.
Mhm.
What we did is we took a fixed epsilon, so we said maybe we wanted the difference to the limit to be less than that distance. Okay, so we know that from this point on, the distance to the limit is less than that distance. Okay, so here's the limit, and here's a lower bound, here's an upper bound. Okay. So we know at all points after this point, the sequence must be below this top line. Okay, because it's converging. And then there are some points before this vertical line. We take a maximum of those, like that one. Maybe it's up here somewhere. And all points we're below. Before the line, we're below that one. So at all points in time, we're below the maximum of these two lines.
Okay. Getting there.
Slightly confusing because I should have done this first, really. It's a separate thing. But, let me just run through that whole proof again. Just making it. So just forget about everything over here for now. Okay, and we'll just do that boundedness. Okay. So what we want to prove is that suppose xn tends to L as n goes to infinity. We want to prove that there exists some bound in R such that for all n in n, xn, absolute value of xn is less or equal to the bound.
Okay.
Okay. So if we have a convergent sequence, for any convergent sequence, there is a bound. So any convergent sequence is bounded. Okay, that's for clone. So what did we do? Well, the first thing we did is we said we used the definition of convergence. So we took epsilon equals 1 in the definition of convergence. So that means that there exists some n in n such that for all little n greater or equal to big N, xn minus L is less than 1. Okay, it's just straight from the definition of convergence. And remember that xn minus L is less or equal to the absolute value of xn minus L. It's less than 1. So xn is less than L plus 1.
Okay.
Likewise, mistake last time possible. Yeah, I think there was a little mistake in the last time I did it. I'll do it right this time. Okay. So this is fine. We also have that L minus xn. Well, that's equal to minus xn minus L. Which is certainly less or equal to the absolute. Does that make sense? So, if xn minus L was minus 3, right, so if this is negative and these two things will be equal, but if this is positive then this will be strictly less than, okay? Which again, this thing is less than 1. So L minus xn is less than 1, so L minus 1 is less than xn. So xn is less than L plus 1 and it's bigger than L minus 1 for all n bigger or equal to this capital N. So the absolute value of xn must be less than So if how do I explain that?
So I'm just trying. I have understand until the last one.
Yeah, until
One step before that. So how do we end up with saying that the absolute of xn is less than max? I'm just struggling to understand the last line.
Yeah. I was just trying to think how I could explain it. Well, we know that so we know that xn is less than L plus 1. We know that L minus 1 is less than xn. This one implies that 1 minus L is greater than minus xn. Okay, so we've got, this is an upper bound on xn, this is a lower bound on minus xn.
Okay.
So let me do it. Where was this? What was this? L minus 1. L minus 1 is less than xn. So what have we got? We've got 1 minus L so xn is less than 1 plus L, minus xn is less than 1 minus L. So the absolute value of xn must be bounded by either that one or that one. It must be bounded by the maximum of the two. Does that make
So
sense?
the first, it is the upper bound, right? So
Yeah.
xn should be lower than that. And the second one, it is the lower bound, right?
Well, it's a lower bound on xn, but it's an upper bound on minus xn.
Oh, okay.
Yeah, so minus xn has to be less than 1 minus L. So the absolute value, so if we take the absolute value of xn, well, if xn is positive, then the absolute value of xn is equal to
It should
xn,
have, yeah,
so it has to be
max,
less
yeah.
than 1 plus
Yeah.
L. If xn is negative, then the absolute value of xn is minus xn, so it has to be less than 1
So
minus
it is
L.
again upper bound. That's why you, okay.
Are you having lunch break?
Like one bit after 1.
Okay,
1:30.
we're going to lunch now.
Okay.
Did you get
What
something
is,
to-
oh, okay.
We're a bit late starting. Yeah,
Okay,
okay,
I
so that
got
makes sense.
Okay, yeah.
Okay,
That's
so-
why you put max.
Yeah,
Okay.
yeah. So xn is less than the max of what was that? 1 plus L, L plus 1, and 1 minus L. But the absolute value of 1 minus L is the absolute value of L minus 1. It's funny. I can write these things without thinking, and then actually remembering where they come from takes
Yeah.
a second. Okay, so we've got some bound on xn, but this is only true for n bigger or equal to capital N. Okay, so can I rub? Well, I'll just rub out this stuff a little bit. So for little n bigger than capital N, we have this bound on xn, but capital N is finite for only finitely many points less than capital N. Okay, so let's take m equal to the maximum of the set xn for little n less than capital N. This is a finite set, so it has a maximum. Okay, then for all n less than capital N, let's take the maximum of the absolute value of xn. That's what I mean.
Yeah.
Yeah. The absolute value of xn is less or equal to capital M. Okay, so then let's take b equal to the maximum of m and what we have down here, so absolute value of L plus 1, absolute value of L minus 1. Then for all n and n, absolute value of xn plus whatever you. So we took m as the maximum for n less than n. So for any n less than n, xn must be less or equal to the maximum. So if we take b as the maximum of this m, this maximum for the first finitely many elements, and the previous bound we had, L, absolute value of L plus 1 and L minus 1, then it must be true that for any n, xn, absolute value of xn is less equal to b. Because for any n, either it's less than n, in which case it's less than m, or it's bigger than capital N, in which case it's less than this thing. So in any case, it's less than this band. Okay, so this means that any convergent sequence is bounded. Okay. Yeah, because it's bounded, it also has a least upper bound. Okay. So it's a useful property that gets used reasonably often. You know, it's kind of obvious, right? If a sequence is going to converge, it has to be bounded. If it was, you know, a sequence that isn't bounded, I don't know. You know, here this is clearly not bounded. We're getting bigger and bigger, but it's also clearly not converging. So going back to what we were proving originally. Okay, so remember we had xn converging to L, yn converging to M, and we wanted to prove the product of xn and yn converged to the products of the limits. We're taking epsilon greater than 0, and we knew that there was some n1 such that that held, n2 such that that held, and we took n as the maximum of the two. So for little n bigger than capital N, we had this, and we got as far as here. Yeah. So now, this was what we were working on. This was the problem. So let's take capital B as the bound of xn. Okay, we know xn is bounded by some number. Let's just call it capital B. Okay, so this is strict. This is strictly less than b. So this thing is less than b. Yn minus m is less than epsilon. Plus m is just some constant. Xm minus L is less than epsilon. Okay, so this is b plus absolute value of m times epsilon. Okay, and just as we did for the addition case, we can kind of change our proof a bit. We can delete that line and start by saying let e greater than 0, and then let epsilon equal e divided by b plus absolute value of m. Okay. And with that definition, kind of redefinition of epsilon, this then becomes e. Okay, so we've proven that this distance is less than a. Does that make sense? Okay, I don't know. Too much. I wrote down too much. So the last thing we wanted to prove so we've done it for linear combinations, so for sums, we've done it for products, we just wanted to show it for ratios as well. Just good practice. Xn over yn tends to so do you want to have a go at this case?
For the product, right?
For the ratio.
Yeah. Or maybe I can do it during the break and we can.
Okay, and move on.
Yes, whatever you want.
Well, no, it's simple. We should do it now.
Okay. So.
I'll send you some other exercises.
So if we take xn over yn, right, minus L over M, so this
Yeah.
will be absolute.
Yeah.
And so now I suppose we have to multiply, right? Or no? Oh no, we have to add and.
Subtract. Yeah, maybe. Yeah. Yeah, let's try that. So what do you think we might add and subtract?
No, let me think about it as well. I don't know if it should be add and subtract or if we need to multiply and divide, because I think that the second fits better, but if let me think about it. No, I'm stuck now. I need just to do it many times.
Well, make a guess, and we'll see what happens. So what we want, so we either want like an xn minus L together, or a yn minus M together. But because yn's on the bottom, it's going to be hard to get a yn minus M together. But we can get an xn minus L together. So if we do.
Okay, so if we do minus L over yn, right? Yes.
Yeah, exactly.
Okay.
Yeah, that's it. Okay, so now what are we doing?
We take the triangular.
Yeah, exactly. So now this is my ones and my L's look the same. So this is so this bit's a bit horrible. This bit's okay. So how are you going to deal with these two terms?
Well, the second term is less than epsilon, right? So we have to deal with the first one only.
Yeah.
Yeah, with that, yeah. But
So we'd like this to be bounded.
yeah,
So if this was bounded,
yeah.
then we'd be fine.
But
And then to deal with over here, we have to prove that
I will
what-
be
1 over yn. So if we can prove that 1 over yn converges to 1 over m, then we know that that will deal with that term. it will also imply that 1 over yn is bounded,
Okay.
and then we're done, right? So all we need to do is to prove that 1 over yn converges to 1 over m.
Okay. Okay. Yes.
So we haven't actually used that yet. So let's just. So this, if you like, is another sub-proof that we have to do. We're going to need a different n, aren't we? So we've got that yn tends to m as n tends to infinity. We want to prove that 1 over yn tends to 1 over m as n tends to infinity.
Okay.
Okay, and we're going to need the m not equal to 0. Otherwise nothing's going to work.
Yeah. Yes.
Yeah. Well, just as before, we know that if an epsilon greater than 0, then if there's capital N. It's not so easy, is it? Okay, when we want to get to something on 1 over yn, a bound on that. To be honest, I don't completely remember how you do this, but let me just try something.
Yeah.
So normally when you have a fraction with two different bottoms, it helps to get them both onto the same bottom. Okay, so this is m minus yn over m times yn. That looks a bit better already, doesn't it? That's right. So we can, with absolute values, we can always flip the sign. Yeah, this is just the same as yn minus m over yn. So we have something nice on the top now.
Okay. Yes.
Yeah. Okay, so this is less than, well, this is equal to absolute value of yn minus m over absolute value of m, absolute value of yn. Okay, this is fine. But top thing is less than epsilon. This is just a constant. Absolute value of yn is bounded, but it's not. So we're trying to make this bigger, right? To get something that's bigger than it. So we're trying to make that bigger, or equivalently, we're trying to make the bottom smaller. So what we need is a lower bound on the absolute value of yn.
Why lower?
Because we're trying to. So we want to write that this thing is less than something. Okay, so we have to make the whole thing, to get from here to here, we have to make the whole thing bigger.
Okay, so we want that to be bigger.
Yeah, so we want to make this bit
smaller, so
yeah, exactly, because 1 over. Okay. So we want to make the top bit bigger, the bottom bit smaller. So we need a lower bound on the absolute value of yn. But Okay, so the absolute value of yn is always at least greater or equal to 0. Let's assume that it's never exactly 0, because otherwise it wouldn't be well defined anyway. So we need, let's just put it up the top as another assumption, yn never equal to 0. So then 0 is a lower bound for the absolute value of yn. Okay, because every element is bigger than 0. So by the continuity property of the real numbers, if it has a lower bound, it must have a least lower bound, an infimum. So we can just take the infimum of the set yn n in n. Does that make sense? And let's just call this thing, let's just call it little b. Okay, equals epsilon over absolute value of m little b. So then we're done. Yeah, we go back to slightly change our start. We start by saying let e greater than 0, and we define epsilon equal to e times m, absolute value of m b. Okay, then we're done. Mathematicians sometimes do a box at the end to say this completes the proof. That's kind of end of proof. Yeah, okay, so what we've proven here is that, well, it's obvious, isn't it? So we've proven that if yn tends to m, then 1 over yn tends to 1 over m. In fact, we don't need to do anything over here, because we previously showed that if xn, we previously showed that it works for products, right? So now what we're doing to get xn over yn is just the product of xn and 1 over yn. See what I mean?
Yeah.
So using this result and our previous result. We're done. These are some of the building blocks of convergent sequences. Tomorrow we'll look at limits of functions, and we'll learn a few other ways of working out limits. Okay, so these are quite these results are useful, but there are even more useful results which make it faster. I think we're going to go into series, are we? Let's at least try and finish this chapter. Okay, so these are some properties of convergent sequences. Another useful one is this one, the sandwich theorem. This says, can you read that okay? Yeah. So if you've got yn tending to L, you've got Zn also tending to L, and at all points in time yn is less than xn is less than Zn. Okay, so if you like, yn is always a lower bound, Zn is always an upper bound for xn, and these bounds are kind of converging together over time, then it must be the case that xn is tending to the same limit.
Oh, okay.
Does that make sense? It's kind of a picture it looks like. So maybe here's our yns, here's our zns converging to the same point, then x is somewhere in the middle. It might be doing something crazy, but if it's always between those two bounds, it has to converge to the same point. Yeah, the proof is kind of immediate. We have the absolute value of xn minus L. Well, that's equal to equal to L minus xn I'll do it the way they did it. Sorry. Let's just do their proof. So just as I said previously, absolute value of x minus L less than epsilon, well that means that x is between L minus epsilon and L plus epsilon, just as we showed before. So, I can't read that. So, okay, so we know that we can find for not large enough n, yn minus L is less than epsilon, and zn minus L is less than epsilon. Okay, so yeah, ignore that. We can do it clearer. So yn minus L is less than epsilon. Okay, because yn minus L is less than the absolute value of yn minus L. And this thing is the same as L minus Zn, remember? Okay, so L minus Zn must... Have I got upper and lower the wrong way around? Yes, I have. Sorry. Okay, we do it again. So this is the same as L minus Yn. So this is L minus Yn less than epsilon. And this is Zn minus L is less than epsilon. L minus epsilon is less than Ym, and Zn is less than L plus epsilon.
Okay.
That makes sense. So L minus epsilon strictly less than Yn, but Yn is less or equal to Xn, which is less or equal to Zn, which is less than L plus epsilon. Okay, so L minus epsilon is less than Xn is less than L plus epsilon. Okay, so this is just the same as saying the absolute value of Xn minus L.
Okay, yeah, yeah.
There's a full proof on this page. So, for example, if you've got some convergent sequence going to 0, Yn, and Xn minus L is always less or equal to Yn, then Xn must converge to L. And this just follows from sandwiching. This inequality is it's just the same as L minus Yn is less or equal to Xn is less or equal to L plus Yn. So this is sandwiching Xn between L minus Yn and L plus Yn. But we previously showed that linear combinations go to linear combinations. So this is converging to L, this is converging to L, so this must be converging to L. We'll skip the examples for now. Okay, so one more thing on sequences. So we say that a sequence is increasing if Xn plus 1 is bigger or equal to Xn. Okay, so it's weak increasing. Xn plus 1. So if it's a strict inequality, then we say it's a strictly increasing sequence. But otherwise, we just say it's an increasing sequence. Decreasing is the opposite, obviously. And if it's either increasing or decreasing, we say it's monotone. So monotone just means always going in the same direction. Okay, so it doesn't matter if it's up or down, but it's always going in one way or the other. Yeah, so 1 over n is decreasing, obviously. a constant sequence is both increasing and decreasing.
Okay. Mm-hmm.
Yeah, because it's weak.
Yeah,
Weak
yeah.
inequality. Stupid lights just turn off. You have to jump up and down. There we go. They sometimes think you don't exist. Minus 1 to the n is not monotone because it's jumping up and down. Okay, it's not getting in the direction. And this is quite an important theorem. If a sequence is increasing and it's bounded above, then it's convergent. Okay, so that gives you, yeah, and it converges to its supremum, its smallest upper bound. Likewise, if it's decreasing and bounded below, then it converges to its infimum. And you know, it kind of makes sense intuitively, right? If you've got a sequence and it's going,
Yeah.
yeah, it kind of looks like it's converging to its infimum. Can we do this? Okay, so to prove that, so we're supposing that for all n in n, xn xn plus 1 is bigger than xn. Okay, so it's an increasing sequence. Okay, we want to prove. Oh, it has to be bounded as well, isn't it? So we're supposing that, and we're supposing that xn is less or equal to b. Some upper bound. Okay. Okay, so because it's okay, and we want to prove that xn tends to the supremum of the set xn n in n. So let's call, rather than writing supremum 1,000 times, let's let's just call it, let's x star be the supremum. Okay, the supremum, we only know the supremum exists because x is bounded above, right? If x wasn't bounded above, it wouldn't have a supremum necessarily. So, from a definition of a supremum, we know those two facts. So we know that for all n in n, xn is less or equal to x star. Okay, that's just saying that x star is an upper bound. And we know that for any z, let's say less than x star, there exists some n in n such that x n is greater than z. Okay, so here in the definitions of supremum that I showed you earlier, it was for all s in the set of elements s, but because the set of elements are just indexed by n, so we can just rewrite it in this way. Does that make sense? Yeah. So we know this, and we know it's increasing. We want to prove something about convergence. Okay, so let's start, as we do every proof about convergence, let's start by setting epsilon greater than 0. Then So we're going to need a capital N, but we don't know what capital N we should take yet. So let's just see how we go and see if we can work out what the capital N needs to be. Okay, so the absolute value of xn minus x star, we kind of want that to be less than some epsilon. We want that to be less than epsilon. For sufficiently large n. Well, if this was true, then we know that x star minus epsilon is less than xn is less than x star plus epsilon. Right, it's the thing you see lots of times. Okay. So xn is in that interval somewhere. So x star minus epsilon is something that's it's less than x star. We could find an n look at the proof in the text, look a second. Oh, because it's increasing. Okay, yeah, that's fine. Okay, I know what's happening. Okay, so if we look at, just go back to this definition from the Suprema, we said that there exists an n such that xn was bigger than z. Okay, but because the sequence is increasing, we can kind of rewrite this. We can rewrite this condition to include 2 dash as for all z less than x star, there exists, let's call it now capital N in N, such that for all n greater or equal to capital N, xn is greater than z. Do you see how this follows from that and the fact that it's increasing? You know, for some n such that xn is bigger than z, then xn plus 1 is also bigger than z, xn plus 2 is also bigger than z. Into the distant future is always bigger than z because xn is increasing. So once we found one element xn bigger than z, we know that every future element is also going to be bigger than z. So we can rewrite it like this. Does that make sense?
I'm trying to find what's the diff for every n again.
Yeah. So there was a particular n with xn bigger than z. But now we said there's some big n such that for all little n bigger than big n, xn is bigger than z. Okay, so this is because xn is increasing. So let's start with proof proper. We let epsilon bigger than 0, as I said, and let's take z equals to x star minus epsilon in 2 dash. Okay. Then what we know is that there exists n in n such that for all n bigger than n, xn is bigger than x star minus epsilon. What am I doing? Yeah, that's fine. But we know that xn is less than x star because x star is the suprema. Okay, so we have x star minus epsilon is less than xn is less than x star, which is less than x star plus epsilon.
Yeah. Mm-hmm.
Okay, so this is absolute value of xn minus x star. Oops, x star is less than epsilon. Thick. Does that make sense?
Mhm.
Is that clear? So, increasing bounded sequences converge to the upper bound. Okay, we've done all that. Yeah, okay. Okay, this is useful. Did I do it properly? Well, no, we'll do it. Okay, there's some examples that we're skipping. I'll go back and find some exercises for you once we get to the end of the chapter. Okay, so I think we're just a few more little theorems to show. So this is kind of almost trivial. A sequence can have at most one limit. So, you can't have, if xn, you can't have both xn tends to L and xn tends to M where L doesn't equal to M. So what this proof does is, well, suppose that xn tends to L and xn tends to M. Let's prove that L equals M.
Okay.
So they take epsilon bigger than 0. Well, it's not, I'll write it again. So we've got L minus M. Well, let's add and subtract things. That's L minus xn plus xn minus M. Okay, which by the triangle inequality is less or equal to value of L minus xn plus absolute value of xn minus M. We can always find sufficiently large n such that this is less than epsilon and this is less than epsilon. Okay, so this is less than 2 epsilon.
Yeah.
But epsilon can be taken arbitrarily small. Okay, so we can make the difference between L and M arbitrarily small, therefore L equals M.
Okay.
Yeah, yeah. Take epsilon is 0.0000001.
So,
Yeah. Straightforward. So sequences only have one limit. So if you can yeah. It seems like a trivially obvious thing, but it's a result that you still have to use occasionally. What's this? So this is just a result about if every element of a sequence is bigger than A, then the limit is bigger than A. Again, it's quite intuitive. So. Well, okay, so we're supposing and that xn tends to, this is for all n, and that xn tends to L as n goes to infinity. Then okay, then because this converges, we know that as ever we let epsilon greater than 0, then there exists n in n such that n greater than big N. Absolute value of xn minus L is less than epsilon. Okay, so this is, we can rewrite this as we've done before as L minus epsilon is less than xn is less than L plus epsilon. But we know that xn is less or equal to a, so this is L minus epsilon is less than xn is less than a. Yeah, we're just ignoring that. Oh, it's bigger than. Sorry, I've got it the wrong way around. Sorry, xn is bigger than a, so this is, we're ignoring this bit.
Okay.
We're taking a less or equal to xn is less than L plus epsilon.
Okay.
So a is less than L plus epsilon. This is true for any epsilon. So it's true for arbitrarily small epsilon. The only way it can hold is if a is less than L.
Okay. Okay.
Yeah, other important things. Any convergent sequence is bounded, we already proved. We did that one. So a sequence that doesn't converge is a divergent sequence. So any sequence that doesn't converge is divergent. It doesn't necessarily mean it's unbounded. Okay, minus 1 to the n, 1 minus 1, 1 minus 1,
Yeah.
1. Yeah, that's divergent, it doesn't converge, but it's also bounded. Right? So all convergent sequences are bounded, but not all bounded sequences are convergent. This is fine. Okay, we better stop there. I think
Yeah.
I've tortured you enough. Let me give you some exercises to have to go around. So we should do something with proof by induction. So what about these ones? 3.11. Yeah, so have a go at 3.11 exercise 1. And maybe 2 as well, because this comes up in economics a lot. Okay. Don't worry about the rest. So 3.11, 1 and 2.
Yeah.
And then from 4, any others from 3? Okay. What's the exercise? Yeah, so that looks okay. So 4.6, 1. 4.6 on part 1. Can't read that. yeah, do 2 as well. Do 1 and 2 here from 4.6.
Okay.
You know, see how you go. If you
Mhm,
if you
mhm.
find that the first of those proof by inductions takes too long time, then don't bother about the
Okay,
rest. You know,
mhm.
but try and do a bit of everything. But there should be some more exercises. You see the exercises?
Yeah, here.
Oh, here,
36,
okay.
Yeah.
Have a go with number 3.
And 420.
423. Doesn't seem too horrible. Can you do? That's what he follows from one of the examples. Oh man, these look good, don't they? 429.1. That's useful. Yeah, 429.1 and 2.
Mhm.
3 as well, though 3 requires something we haven't actually done yet. So we write that xn goes to infinity as n goes to infinity. What this means is that, because infinity is not a real number, it needs a separate definition. So does not mean xn converges. Right, this is xn diverges to infinity, is what you'd say. The definition of this is that for all k greater than 0, there exists n in n such that for all n greater or equal to n, x n is greater than k. And there's an analogous definition for minus infinity. Okay, it's just swapping the signs. So rather than having an epsilon, small epsilon, now we have a k which is going to be big potentially. So for any arbitrarily large k, we can find some big N such that for any little n bigger than big N, xn is going to be bigger than k.
Okay.
So for any upper bound, you know, eventually the sequence is always going to be higher than it. So that's what it means to converge to infinity. So yeah, do exercise 3 here as well, which is about convergence to infinity.
You said 1, 2,
Yeah,
and 3.
1, 2, 3.
Okay.
If you have time, carry on. Do 4 as well, but we'll see how you go. Yeah, but so if you still have time, do the rest of these. But I guess you probably won't. Okay, I think I've tortured you enough. So I'll see you at 5 to go over some exercises. If that's okay.
Okay, thank you.
Okay.
So I need to go and find the book maybe.
So, where did you get stuck?
So, this one. Could you open
Yeah.
the book so I can tell you the pages? Okay, yeah. Okay, so the first.
Why don't you keep a book and I'll look at this
mhm.
and then we can. It's easier. Let's just turn the projector off. That's really easy. Do you want to go on?
Okay, so we proved that,
Oh yeah.
but I did it again, and I did it in a different way because I tried first to do it myself, and then I looked at your proof, and I see how you did that, but I just tried to do it as we proved this one.
Oh, directly.
Yeah, and I tried to do that way, but it didn't really work. Have you tried that? For example, if I do the same, or I cannot do it.
It's possible you could do it that way.
But if because here there is a mistake. If we can do it that way and I just do it like this, then I can put greater or equal and put that plus because this should be minus, right? So minus minus it is plus from this theorem here.
Okay, so you're trying to make it small. No, because you're trying to make it smaller.
Mhm.
So yeah, this is smaller than that. Minus this is smaller than minus that because
So CD is less or equal to absolute value of CD, isn't it?
Mhm.
So minus CD is bigger or equal to minus absolute value of CD.
Okay, so this is
it-
okay, so this is less than, as you say, less or equal, right?
No. What you'd written
Ah.
was right.
So greater than, yeah,
Yeah.
same it is here. Greater or equal, but this is minus, so it should be plus this.
No, but this was with a minus. Minus CD is bigger or equal to minus absolute value of CD.
Which is so minus CD is bigger or equal to minus absolute value of So I think what you had was right.
Ah, okay. Okay, I was trying to follow this, that's why I was maybe confused.
Oh well, that's also.
Well, that's not true. Okay, so, well, it's also the case for minus CD. Yeah, okay, so maybe that works. Minus CD is less or equal to absolute value of CD as well. So, you can.
Let
Is
me.
that what you want?
Yeah, let me put that down and I will try it once again later.
Maybe. Let me just have a. So you want to make it. You want a lower bound. So your idea was to use this.
Yeah. And then I was confused with the signs.
Well, maybe you can put a minus sign inside. So you need minus CD bigger than something.
Yeah.
So what we're trying to do. So you're trying to get what absolute value of C minus absolute value of D, all squared. Right. That was what you were trying to get to.
Yes.
So this is absolute value of C minus 2 times absolute value. Sometimes it helps to work from both sides to see what you need. So this is isn't that what you had to start with?
Yeah, I had to start with this and get to that.
No, so this was a minus sign. It was all right. wasn't it?
Okay. Yeah.
I think it was right
If
to
it
start
is
with.
like this, you
Yeah.
come to the result. But maybe I was then confused with this theorem here because I thought that if you are here, it is larger by minus. So I thought minus it will be.
So this theorem says that
That theorem says minus absolute value of CD is less or equal to CD is less or equal to absolute value of CD.
Yeah.
So if we take a minus sign all the way through, that says CD is greater or equal to minus CD is greater or equal to minus absolute value of CD.
Yeah.
So we just flipped all the signs and put a minus sign in front.
You know what I did? Yeah.
So
What I did
minus
was-
CD is bigger or equal to absolute value. of
Yeah. Yeah. Okay. Yeah, because what I thought was that we have CD and then I took minus absolute CD, so it was minus plus, which was wrong. Yeah, I see.
Okay.
I
But
see why.
Yeah,
Yeah.
the absolute value of minus 1 is still 1.
Okay.
This was that kind of mistake.
Okay. Thank you. I will do that again. So the next one was about. I just want to make that a bit more clear about the upper bounds and the lower lower bounds, because I was confused with these examples. We have a set 1, 2, 3, which is bounded above and lower, right?
Yeah.
And it says that some upper bounds are 110, 4, and 3. Why is that? Some upper bounds, we have one set 1, 2, 3, so the upper bound will be 3, no?
That's the least upper bound.
Okay.
But so an upper bound is, remember for the supremum we had those two properties, and the first one was for all S in S, so B was our bound, S is less or equal to B.
Yeah.
So anything satisfying this is an upper bound. So an upper bound is just something which is bigger than all of the elements in the set.
Okay.
So, that set 1, 2, 3, 100 is bigger than all of those numbers, but so is 1,000.
Okay, yeah, but because the 100 or 1000 is not within this set, that's why.
So a maximum has to be in the set.
Ah, okay.
So that's the difference. So B, B is just some number in R.
Mhm.
Okay, to be an upper bound. If it's a maximum, then it has to be in the set.
Okay.
But
okay.
many sets don't have a maximum.
Yeah, I found that, yes. Okay. And then what else? Page 20. Okay, so when we go to chapter 3 and we start with natural numbers, the whole chapter takes that 0 is not a natural number.
Yeah.
And some theorems are based on that as well. So I just
It's not going to make too much difference. I gave it to you with 0 being a natural number because almost every other textbook you'll see will have 0 as a natural number. So it seems to be an oddity of that textbook. Most people have 0 as a natural number, but proof by induction say it doesn't really matter if you start by proving the case for 0 or if you start by proving the case for 1. The idea is still the same.
Okay. I will try with 1 then. Okay. And the principle of induction. What is chapter 3 as well. We said that we need to prove. Well, here in the book says that P1 needs to be true.
Yeah.
And we said that P0 needs to be true. So when do we take P1 or P0?
Well, it doesn't. So as long as. So if you want to prove that it's true from 1, 2, 3, 4, 5, 6, then you start with P1. If you want to prove it's true from 0 to 1, 2, 3, 4, 5, 6, then you start with P0. It's always going to be true from the point you start onwards. It doesn't really matter too much where you start.
Ah, okay, so you can start from P5? Or?
Yeah, if you want to. So if you started from P5 and used this, you'd prove that it was true for 5 and above.
Ah, okay. Okay. And then, okay.
So you can start where you like, really.
Yeah.
I was starting at 0 because my natural numbers were starting at 0. But you can start at 1.
Because I found out in the exercise I did for this chapter, and for example for exercise 2, I had to take P0 instead of P1 because I could do
it was easier with P0. Okay.
So, yeah. And so
often it's easier starting with 0 than with 1, to be honest, because 0 is normally a trivial case. And
okay.
It's very easy.
Okay. And then I finished with that exercise in chapter 3, where what is it? The second exercise I did. So I took it to a point, and I don't know if this is it or I need to continue it.
Okay. Well, do you want to have a go on the board? Explain what you did? It seems like a lot of...
No, it just, I took this P0 because for P1 it didn't work, and then I took P0 as we did, so it is true. And then we take Pn plus 1 to see. And I have, if I do this formula, I take this formula here, the big one. I delete this, and we have this one here which says, I left it empty because I didn't have that much time to do it. So this is it, I just leave it there, or?
So how are you, you're factorising?
So I try to prove if Pn plus 1 is true. So I take it to that step here.
And how do you get from there to there, sorry?
If you use this formula here...
Oh, but that's what you're supposed to be proving. It says deduce that for any real numbers A and B. So it wants you to prove this, and then use that to prove that.
Oh, really? I thought they gave that...
No, they're not so nice. Okay, well you started right, so should we have a go at that?
Yeah.
So it's the sum from k is 0 to n, x to the k, and the claim is that that is equal to 1 minus x to the n plus 1 divided by 1 minus x. Okay, so you started by saying when n is 0, this is the empty sum, so this is just 1, so when n is 0, this is just the claim, but 1 is equal to 1 minus x to the power of 1 divided by 1 minus x, which is, yeah, okay, so when it's 1, it's, when n is 0, it's easy. Okay, so we want to suppose it's true for n, and we want to prove it's true for n plus 1. Okay, so you started the right way. Okay, so here's our n plus 1 case. That's what we're interested in. So that's sum k is 0 to n, x to the k, plus this extra term, which is x to the n plus 1. And when you're doing proof by induction, you always have to use the inductive hypothesis somewhere. So the inductive hypothesis is what you're assuming at each step. Okay, so here we're assuming that sum k is 0 and x to the k is 1 minus x to the n plus 1 over 1 minus x. Okay. So we assume it's true for n. We want to see if it's true for n plus 1. So this is called the inductive hypothesis when you assume that. So here we've got a sum k is 0 to n x to the k. So we can use the inductive hypothesis there. Okay, so we know that this term is equal to that. So we can just plug that in. So that's 1 minus x to the n plus 1 divided by 1 minus x. And then we still have this extra term, which is plus x to the n plus 1. And what we want to get to is, well, we want to get to 1 minus x to the n plus 2 over 1 minus x, which is what you had. So we're going to need to factorize a bit, or try and, well, we need this to be over the same fraction. Okay, so we can write this as 1 minus x to the n plus 1 over 1 minus x. So what's this going to be on top?
1 minus x, yeah, times x, yes. So it will be xn plus 1 minus xn.
Plus 2.
Is it?
So we've got
yeah, minus,
x to the n plus 1
Mm-hmm.
times another x, so that's x to the n plus 2. That's an x, believe it or not. So we've got 1 minus x to the n plus 1, we've got a plus x to the n plus 1. These two terms are going to cancel out. Okay, so that's just equal to 1 minus x to the n plus 2 over 1 minus x.
Yeah.
And that's what we wanted to get to.
Yeah.
So we've shown if it holds for n, then it also holds for n plus 1.
So we are done with that.
Yeah, that's it.
So we stay there, right?
Yeah.
Okay. Okay. And then we have to prove.
Deduce that for any real numbers a and b. A to the n minus b to the n. So how do we get from there to there? Well, have you got any ideas how we can get to the equation it said?
Is there any way of getting the equation it gave us there into the form that we've just worked with?
So we have to prove that.
Yeah.
Wow. Okay.
But it follows. It's going to follow immediately from what we've just proved. But there's just going to be a trick to getting it into that form. So.
You mean to create a, because we have 1 minus xn, so it is kind of an minus bn.
Yeah, similar, yeah. So say we wanted, okay, so we wanted 1 minus x to the n, well let's, okay, so we wanted 1 minus x, let's stick with plus 1, so it's the same. Oh no, I'm sorry. Okay, so we wanted 1 minus x to the n to be equal to a to the n minus b to the n. Well, it's not going to be equal to, is that? So I don't know how to write it without giving you the answer. So we're going to have to make a transformation to one side or the other. So in order to get, so we've got a to the n minus b to the n, and we'd like it to be 1 minus something to the power of something. So this bit's got to be a 1. So we can write that as a to the n times 1 minus b over a to the power of n. So that's kind of the trick. Does that make sense? So we just take an a to the n out as a vector.
Yeah.
You know, it's these tricks, but once you've seen them once, you know what you have to do. But they're a bit horrible if you don't know them. So we know that 1 minus b over a to the n, well, that's equal to, from what the formula we had before, that's equal to 1 minus the x here, which is b over a, times the sum up to n minus 1. Sum k is 0 to n minus 1 x, which is b over a, all to the power of k. So that's just from what we proved before, right? We proved before that sum k is 0 to n minus 1 x to the k is 1 minus x to the n over 1 minus x.
Okay, yes.
Yeah, I've just replaced n by n minus 1. So 1 minus x times the sum k is 0 to n minus 1 of x to the k is 1 minus x to the n. Okay, so here we had a 1 minus x to the n. We've just replaced the x, we've taken x as b over a. So we get 1 minus x times this sum.
Okay.
And then, at the moment we've got an a to the n at the front, but we can put that a to the n back in, right? So we can write, let's start with, let's do a to the n minus 1, a minus b. So we multiplied, take an a out of there, put it in here. Sum k is 0 to n minus 1, b over a to the k. And then in fact we can put this a to the n minus 1 over here. So let's just, let's write this as b to the power of k, a to the power of minus k. Yeah, it's on the bottom, so that's negative power. So we've got a to the n minus 1 times a to the minus k. So this is like a to the minus k plus n minus 1. Just delete that.
well. So just rewriting it, a to minus b, n minus 1, a to the power of n minus 1 minus k. I've just reordered it, put n minus 1 in the front, b to the power of k. And I think that's what they had, isn't it? So if you look at what they've got in the book, it's a to the n minus 1 plus a to the n minus 2 times b plus all the way up to b to the power of n minus 1.
Oh yeah.
Yeah.
Okay.
So it's a bit
Interesting.
hard,
Can you just leave it for a while?
oh, okay. So.
Thank you. Okay.
Good, yeah. Does that make sense? Elizabeth.
No, it makes, yeah. It's just the way you should put it down and just try to prove it, yeah, but yeah, I understand your logical, yeah.
Yeah, there's a certain way of thinking as a mathematician, and the only way you can get into thinking like a mathematician is by doing it a lot, so you just have to practice as much as possible.
Yeah, that's why I didn't have the time to do all the exercise, because I was trying what we did during in the morning. I was trying to do it again myself and try to see why.
Okay. So is that the only exercise you tried? Did you try exercise 3.11?
No, because I just started chapter 4.
But did you do the first one from 3.11?
Yes. Yeah.
And that worked okay, didn't it?
Yeah,
You got that fine?
Yeah, it was simple, yes.
Okay. So
Yeah.
maybe she can have a look at your answers for that one.
So, yeah, this one, 1 and 2.
Okay, so here's the first case. So how do you get from there to there?
No, I didn't do the... I took it from here. I just completed this one and then I took this. I don't know if it's right.
So the idea is that you... Okay, so you assume Pn true and you're trying to... Yes, so you're doing the right thing. So Pn plus 1 is that. That's the definition.
I just used this one, yeah, and then I took this, so I didn't do anything.
So you need to... So the aim is that you're trying to prove... you're trying to prove from there to there.
No,
So
actually what I
missed
don't know, yeah, maybe, because I thought that we just put where n is, we put n plus 1. So, yeah, I just used it like here, and then I jumped there, and where n, I just put n plus 1.
Yeah, so
And
this is what we're trying to prove. So you're trying to prove that this thing is equal to that thing.
So it's the right. Well, let's have a go at this
Yeah,
one.
maybe,
Okay.
yeah.
Okay.
So the claim is that sum k is 1 to n squared. What's it? What? K is what am I doing? K is 1 to n of k squared. Obviously, k is 1 to n of k squared is 1/6. Is that right? 1/6.
Yes.
Right.
Mm-hmm.
N plus 1, n plus 2. Okay, so the
It is 2n plus 1. The
Oh,
last,
oh, sorry.
Yeah.
2n plus 1.
Yeah. Mm-hmm.
Okay. So in the case when n is 0, this is an empty sum, so this is 1, and this is, that doesn't work when n is 0, doesn't it? So in the case when n is 1, this is 1,
Yeah. And this is 1 as
and this
well.
is-
Yeah.
this is 1/6 times 1 times 2 times, what's that? 3.
Yeah.
Yeah, okay, which is 1. Okay, so this is good. So in the case n is 1, it's fine. So now, just like you said, we suppose it's true for the case n. So we suppose it's true that this holds. And we want to prove that it holds in the n plus 1 case. Okay, so we're interested in the sum k is 1 to n plus 1 k squared. Okay, well we know that's the sum from k is 1 to n k squared plus the extra term.
Mm-hmm.
Does that make sense? So we just split the sum up into the sum to n and then this last term.
Yeah.
Yeah. And we're supposing that it's true in the particular case of n. Okay, so we can plug in this answer for this bit. So this is 1/6 n plus 1 2n plus 1 plus n plus 1 all squared. And what we want to get it to is we want to get it to what you've written down. So, I don't know, maybe you just did this without thinking. So we've got an n plus 1 here, we've got an n plus 1 there. So let's take n plus 1 as a factor to start with. So we've got n plus 1 times 1/6 n 2n plus 1 plus n plus 1.
Okay.
Does that make sense? So n plus 1 squared, you've got n plus 1, n plus 1, that's 1 plus 1 squared. So, it's not very nice, is it? So this is n plus 1 times 1/6. So this is going to give us 2n squared plus n. So 1/6 times 2 is a third. So let's have a third n squared plus 1/6 n from there, plus another n plus 1. So this is 7/6n. And where are we going? So this is... So what we're trying to get to, let's just write it down so I can remember. So we're trying to get to 1/6 n plus 1, n plus 2, 2n, which becomes 2n plus 2, so 2n plus 3. That's what we're trying to get to.
Yes.
That's what you've written down,
Yes.
isn't it? Yeah. So we've got an n plus 1. So let me get rid of that line and see if we can.
let's take 1/6 out, because we know we have to have a 1/6 in the front. So this is going to be 1/6 n plus 1 times n times 2n plus 1. Now we need to multiply this by 6, okay, plus 6 n plus 1. Okay, we've got 1 over 6 times 6,
Yeah,
which is
yeah,
equal to 1. So we've got the first two terms, right? We need an n plus 2 and a 2n plus 3. So let's, it's not obvious, is it? So I think we have to multiply out the brackets and then factorize. 1/6 n plus 1. So this is 2n squared plus n plus 6n plus 6. Just multiplying out the brackets.
So we have 7 and
Yeah. And we want to, okay, and let's see what happens when we multiply out these two brackets. Let's say n plus 2 times 2n plus 3. I'm not very good at factorizing, so I need to do it. So that gets us, here we get 2n squared, and then we get 3n from there, and then we get 4n from there, and then we get a 6. Okay, and this is the same as that.
Yes.
Okay, so this is what we wanted. So this is 1/6 n plus 1, n plus 2, 2n plus 3. Okay, so we started by assuming that it held for the case of n, just one particular value n. We got to prove that it also held for the case of n plus 1.
Okay, so what I did was not exactly correct because I was just replacing.
Yeah. You see the distinction.
Yeah. Okay. I will do.
So have a go at the second one from 3.11. Using this method. You know, certainly things in econometrics and macro as well that you prove by induction. My wife was an econometrician. She was doing something. She was stuck with something, and we were able to prove it by induction.
Your background is.
Well, I did a maths undergrad and then economics masters, economics doctorate.
Okay, so you have a good background on maths.
Yeah, it helps.
So the induction, what is it exactly?
So induction is this thing that if it's true for 0, and whenever it's true for n, it's true for n plus 1, then it must be true for the whole of all natural numbers.
Okay.
So that's the principle of induction. It's going from those two facts that it's true for 0, and if it's true for n, then it's true for n plus 1.
Okay, so I'm just trying to see practically when could I use that. Because for example now you explain it, I can understand, I can see, but I'm just trying to think where can I use it practically. For example, your wife, you said that she was trying to do that.
Yeah, so we were proving some properties of an estimator. And I can't remember what the example was now. It was like for median. The estimator was so you had a time series like x1, x2, etc., up to xt, and the estimator took them into groups of 3. So you look at x1, x2, and x3. That would be the first group, and then you look at x2, x3, x4. That would be the second group, etc., etc. Then for each of these, you would take the median. Okay, so the one that's in the middle when you order it, and then you wanted to look at the distribution of this median, and the only way we could do it was by doing it by induction on the length of the sequence. Okay, because for a short sequence it was easy to see what the properties had to do.
Okay.
I don't know, in macroeconomics, for something. So in macroeconomics, you'll see this thing, dynamic programming. So do you know what a value function is? It's a long time, I guess. So maybe country is trying to decide how much investment to perform. Okay, its decision is going to be a function of its current capital stock.
Okay.
Okay, so you can write the value of being in a certain state as a function of your current capital stock, and that's going to be equal to I don't know, some utility you get from the consumption because you've got a big capital stock. So some utility function, which here I'm just writing as a function of your capital stock. If you've got lots of capital, then you can produce lots to consume. Okay, and then it's going to be a function of so you're going to, let's write it this way, you're going to choose, today you're going to choose how much consumption and investment to perform. Okay, so you're going to choose consumption and investment to maximize your utility from consumption plus beta, some discount factor you care less about in the future, times your the value you're going to have tomorrow. So you get some utility today, you're going to have some utility in the infinite future. So, and tomorrow's capital is maybe today's capital minus some depreciation plus your investment.
Okay.
Okay, so a firm is choosing consumption and investment in order to maximize this thing, a combination of their consumption today and their discounted future consumption, discounted future value. So it turns out that this is equivalent to maximizing the sum of t, I don't know, t is 0 to infinity, beta to the power of t, u, ct, where ct is the amount of consumption you perform in period t. Subject to a budget constraint, okay, but consumption plus investment, I should really use the lowercase. Consumption plus investment is equal to, you'll do this in macro, is equal to your production, okay, which is, I don't know, some function of your capital stock, and KT is so this is one way of writing down the problem. Okay, so today you're just choosing consumption and investment to maximize this combination of your utility today and your future value. So your value today is a function of your value tomorrow.
Okay, yeah.
Yeah, so it's kind of recursive representation of it. This is just another way of writing down where your value is your value is this infinite sum of all future periods. Okay, and this representation is equivalent to this representation, and well, the way you prove this is via induction. Or one way you could prove it would be via induction. So think of, maybe I've made it too complicated. If you had or I don't know, so here's something we can prove by induction that's actual of some relevance. Suppose you've got what's called a cake eating problem. So I've got a big piece of cake in front of me, I'm going to live for so many periods. Suppose I'm going to live for capital T periods. And my utility in a particular period is some function u of the amount of cake that I eat.
Mm-hmm.
Okay? And I just care about the sum of my utility for all the periods that I'm alive. So maybe I'm alive from 1 to t. So I care about the sum, t is 1 to t, of u ct, where ct is the amount of cake I eat in period t. And there's a budget constraint, which is I can't eat more than all of the cake. Okay, so the sum of all of the amounts of cake I eat in a particular period has to add up to 1, the size of the cake. Okay, and maybe let's simplify things a bit by taking u of c is just square root of c, so we've got a functional form. Okay, and let's look at the claim in period t. Ct. I don't need to write it down. So we're going to look at the claim, but in the last period, you're going to eat all the rest of the cake. Okay, it seems obvious, but still something you need to prove. So the claim is that Ct equals sum t is 1 to t minus 1. Ct. Okay, if that's the amount of cake, sorry, 1 minus. Okay, this is the amount of cake you've already eaten up to that point. 1 minus is the amount of cake left.
Yeah.
Okay, so our claim is that in the final period, you eat all of the remaining cake. Well, can we prove this? You know, it's not obvious how you prove this generally, but let's take t as 1. If t is 1, then the objective is just, you know, maybe we don't know how to optimize with sums, okay, then the objective is just uc1, subject to a budget constraint that c1 equals 1. So, well, it's trivial, c1 equals 1. This sum is empty. Okay, so the capital T equals 1 case is easy.
Okay, yeah.
Okay? So suppose that this holds for capital T. Let's see if it also holds for capital T plus 1. So completely sure this works. So if it holds for capital T, I'm just going to change the setup slightly. Let's suppose the cake is of size k for cake. Okay, so suppose this is our budget constraint. So then eating everything in the last period means this. Okay, and we claim this holds for any k. So for all, the claim is that for all k positive, in the last period you want to eat everything left. You want to eat the rest of the cake. So then in our first case, the budget constraint is that C1 is equal to K for any K. So for any K you want to eat all of the cake. This term is empty, so it's fine. So now let's suppose that it holds for T. Okay, so we know that for all K bigger than 0, if you face this problem, okay, then in the final period you want to consume K minus sum T is 1 to T minus 1 CT. Okay, so this holds for any capital K. So let's see what happens if we add another period on the end. So So, I'm not sure you really.
Well, I don't want to make you think so. Yeah. Well,
Sorry, I'm not.
no, I can understand it. I was just trying to think, which is a bit maybe stupid, where we can use it practically. But if we are gonna use it in macro, are we or?
Yeah, so it's kind of in the background behind a lot of the results that Antonio will go through the
Oh,
first
okay.
term in macro. Yeah, it's
Because
so it's in the-
I have understand, yeah, what we did
Okay,
in the
okay.
exercise. Yeah, I was just trying to think why we should, for example, if it works for P1, why we should try for Pn plus 1. Why do we want to prove that? I don't know if you see my point, what I'm asking. Which is not
Okay,
a
so-
problem, it's not...
So, you know, we might know that it works for 1, 2, 3, 4, 5, 6. You know, we might know that it lasts for 1 million,
Yes.
but we won't know that it lasts for 1 billion. And is your point that in practice we only need it to last for 1 up to 1 million, and we never deal with billions or
Yes,
something?
something like that, yeah.
Yeah, so in macro we normally have people who live forever. So normally, because people have children, people care about their children. So it's a simplifying assumption in macro to assume that people live forever. So then you need things to be true for all time. Or in micro theory, you know, people have repeated games of bargaining. And in fact, I think Bimore did some work on this. Where I make an offer, then you make a counter offer, then I make an offer, and you know,
Okay,
bargaining
so
could
yeah,
potentially
yes,
go on
yes,
forever.
mhm,
Okay, in
mhm,
practice, it won't go on forever, but you need to allow for the possibility that it could go on forever.
Okay, I see.
So that's why we need to
Yeah.
work with infinities.
Okay.
This wasn't a very good example. I'm sorry. It's good that you stopped me.
It's okay.
You know, and even if you don't use it directly in economics all the time, it's used in the mathematical theory behind a lot of the economics. Okay, so you'll be, in macro or in econometrics, a lot of what you're doing is you're dealing with infinite sequences.
Yeah, that's true. Yeah.
So if you're,
or when
you know,
you have many data, a very large maybe database and.
yeah. So what you know, we think of a time series like consumption. We think of it as a draw or a short observation from a potentially infinite series of consumption back into the infinite past, back into the infinite future. And you know, maybe you want to prove that your estimate of the persistence of consumption is consistent. Well, for something to be consistent, it means that if you have an infinite amount of data, it still gives you the right answer. So, yeah, so you can't really escape infinities because they're kind of embedded in statistics.
Okay.
I'm not sure if that. You know, so part of the purpose of this course is just to get you used to doing maths and thinking like a mathematician a bit.
Okay, yeah.
You know, it is all useful, it is all very useful, but you know, maybe where things are useful might not be immediately apparent. But,
Okay.
yeah, you know, it's hard to give good examples. What exercise did I ask you to have a look at in chapter 4? Should we just go through one of them?
Yeah, it was.
That one.
We had page 30, 36, and page 40.
That one's on 30. Okay, So the ones on 30 and 36 are less important, to be honest. You know, I guess you don't want to work all night, do you? So I wouldn't look at them. If you